Thanks to the feedback to my Hexemble videos, more specifically the binary exploitation videos where I showed you several pitfalls that can happen during, the basics of exploit development, I got a very interesting suggestion about a case that I also ran into, and it's so frustrating and confusing when you start out. So in this video, I want to showcase another weird issue you might be running into. Hopefully, with this video, you can prevent this from happening. So here's a vulnerable source code example. This time I even developed it myself and then just rip it off Exploit Education. So it's a very simple buffer overflow challenge. The only reason why I'm able to provide this test source code is because I was able to reuse some of the parts from another project that I'm working on. I have actually this startup idea called SAF. It's a C application firewall. It's basically a web application firewall just for C programs. In this case, you get a small sneak peek into what it's able to do. So as you can see, there's a local variable of a fixed size. And then there's this dangerous gets function that just reads input and doesn't care how long it is. And this is where my smart idea comes in. Now you pass this potentially malicious input to the C application firewall function. And this function then goes over this input and then is performing a series of checks that are based on my year-long experience in exploitation. So for example, if somebody tries to enter a lot of A's trying to trigger a buffer overflow, this SAF will detect it. We don't have a release schedule just yet. We are actually right now in the process of raising venture capital. So if you have a lot of money to invest and you look for an awesome, cool project where you just can put your money into and you will not get anything in return, check out my Patreon. Anyway, enough promotion. We don't really care about the code anyway. This is how the binary is compiled. No stack protection, so no stack canaries. The stack is executable and we disable PIE, so the binary is not affected by ASLR. So this is just a very basic buffer overflow challenge. So when we now run the program and we try to create a buffer overflow by entering a lot of A's like you have seen it in the movies, then my SAF will block it. But this firewall has a bug. If somebody is not using A's, I don't know why anybody would do that, but if somebody is not using A's, then you can get a seg fault. But if somebody uses X, it's a very experienced attacker, and this is currently bypassing my C application firewall. And this also leads to a segmentation fault. So let's have a look at that in GDB. Just some settings to make GDB usable. Then we run it and enter our payload. Okay, segmentation fault. This looks good, right? This can already be confusing if you just started out. So if you follow my binary exploitation playlist and you have played around with it yourself, you might be used to an output that looks like this. Program received segmentation fault, cannot access memory at address 545454. And then you get this other line here with the hex 545454 in question mark. And in these episodes, I'm basically telling you that you should use recognizable characters as your input, so then you can easily identify them when you see the memory. And now the 545454 is obviously the ASCII character T, and so you know you have overflown here the return pointer on the stack with T's. So you immediately know this is a buffer overflow. But this output here is different. It doesn't show you anything that looks like the X's that we entered. And it looks like the crash happened inside of the SAF test function. It happened inside of the program. It didn't jump to a fail address of XXX. But there's something else going on, and that's why it can be a bit confusing to a beginner. But there's something else going on, and it can be confusing at first, but it will make sense in a moment. So a segmentation fault always means that a certain piece of code tried to access memory and couldn't do that. It couldn't access memory. This means a seg fault must have been triggered by the current instruction in some way. So every time when you see a seg fault, you want to look at the current instruction where it seg faulted. And when we examine one instruction at RIP or one instruction at that address, you will see it crashed at the ret, at the return. So what does the return instruction do? How can a return crash with a seg fault? So the return instruction always takes a value from the top of the stack and then sets RIP to it. So it basically jumps to the address that was on top of the stack right now. Could it maybe not access the stack? Well, you could check if you can read RSP right now. And yeah, RSP is readable, so it can't be that it couldn't pop the value. But look at the value it tried to pop and set RIP to, 58585858. So yes, ret tried to pop this value from the stack, read that value from the stack, and set RIP to it, and basically jump there. And unfortunately, it caused a seg fault already there. It couldn't set RIP to this address. In these other old school cases here, the ret instruction successfully changed RIP, and then the CPU tried to execute whatever is in RIP, and then it crashed. That's why the output is different. But this means your buffer overflow worked. You overwrote the return pointer on the stack successfully. And if you place there an address that is smaller, that is like a valid address where it could theoretically jump to, then you will also see that it actually will jump there. It's just this huge value, this 585858, that causes a seg fault. So when you get a seg fault, it's either you already tried to execute an invalid address that you tried to execute. For example, in this case here, you tried to execute at 45454, that doesn't exist. But if there is code, then the assembler instruction must have caused a seg fault trying to access memory that was not right. And in that case, you need to look at the registers that are involved in that particular assembler instruction. In this case, return looks at the stack pointer and takes a value from the stack and then sets RIP. And so you need to investigate this. So in this case, we investigated here the stack. But a seg fault could also happen if you, for example, overwrote a pointer or you reach out of an array very, very far away. In such a case, you would probably see a move instruction that caused a seg fault. And when you look then at the registers and think about where it tried to access memory, then you can see, oh yeah, that is invalid memory. Like here, that register points into bad memory that caused a seg fault. So always debug, always carefully analyze the current situation you are in, the current context, and you can do this with examining the memory and the registers. But let me quickly develop an exploit for this. We can overwrite the stack pointer and the stack is executable, so standard shellcode on the stack. So here's the shitty exploit code for this challenge that I've written that includes the issue. I don't want to go into the details of this exploit now because tomorrow's video will be about developing that exploit. For now, I want to focus on the state where you have an exploit and you think it should work, but you run into that issue that I want to show you now. As I have shown you in previous Hacksember episodes about debugging your shellcode, I have prepended my shellcode with a CC, sig trap breakpoint. Watch the video if you haven't seen it yet. So if this exploit successfully jumps to the start of the shellcode and is executing that, the exploit should work, right? Then it starts executing the shellcode. So I started the script, but now it's waiting for my user input. It actually gives me time now to attach to the GDB process. So let's attach. So we are attached and we can continue. And now let's actually trigger the exploit. So we should have triggered the exploit. So let's see what happens. We got the received sig trap. This should have worked. We executed the CC. Now let's look at the code that is supposed to be executed next. So let's compare this to the shellcode and check if it's correct. We have to push 42, pop RAX, increment AH, CQO, push RDX, move that here into RDI. That's actually a string. It's basically bin sh. This looks perfect, right? So let's execute it. Segmentation fault. In 3F here, in 3F, how can a pop seg fault? Pop simply just looks up the value that is currently on the stack and puts it in RSI in this case. That is not accessing weird memory, and this is the pitfall. So let's print 12 instructions from where earlier RIP started. What the heck? This code looks completely different. Earlier it was a pop RSI, is now an add, and here it's referencing memory. You can see RDI is like a crazy number, so that's invalid memory that caused a seg fault. So what happened here? This is one of those issues I remember having run into myself, and this was so frustrating. This issue must have cost me 10 hours or more until I figured out what happened. And the evil thing is that this might have actually worked if you used maybe a different shellcode. It's a very, very nasty bug until you understand what happens. So let's do this again. We start the exploit, we attach GDB, continue, and we trigger it. Okay. So here's our shellcode, and we know looks perfectly fine. But the push instruction affects the stack. The push instruction pushes values on top of the stack and then updates the stack pointer. So where's our stack pointer right now? Our stack pointer right now is here at AF40. This is awfully close to our shellcode. It's just right after here. So let's execute the push. Let's look at the stack again. The stack got updated. The 42 was pushed on top of the stack, and we are even closer to our shellcode. Now we are at R8, just right after our syscall. But we are still fine. If we look at our shellcode here, this still looks perfect. The next instruction is even a pop, which will mean it will pop a value from the stack again, and it will move the stack pointer again further away from our shellcode. So this is all fine. But here we have 3 pushes that follow. You might be able to guess what will happen next. So let me quickly continue executing until we reach the second push here. So we are about to execute this push. Let's have a quick look at our shellcode. Our shellcode looks still good. Where is the stack pointer at? Our stack pointer is just right after the syscall, just 2 bytes away, 3638. And now let's execute this push. Let's look at the stack. We pushed RDI. RDI was this value moved into it. This is basically the bin_sh string. And this string was pushed on the stack. And look where that is now. That is at 30. That's right here inside of our shellcode. So let's look at the disassembly of our shellcode now. Invalid instructions. This push has corrupted the shellcode. So during the execution of the shellcode, it corrupted itself, and thus we ran into a seg fault. And this can be very frustrating just when you started out and you consider that something like this can happen. This is a great example of an issue where you have so many influences and things that happen all at the same time that you need to keep in your head. You have the stack pointer that points into some memory. Your shellcode is right there as well. RIP actually points to the stack as well and is executing this data there. Like, it's a lot of stuff that you need to keep in your head, and only then you will be able to figure out what happens. This can be very frustrating. So in this very old episode that I mentioned earlier, the binary exploitation episode E, I actually got a comment recently by Sean Owell, and he ran exactly into that issue. Implemented the exploit on the buffer and got stuck for longer than I'd like to admit. Make sure that your exploit instructions don't start overriding themselves through stack push instructions. Shortening the knob slide and adding more padding after the exploit instruction fixed things. I now understand why LiveOverflow chose to transfer the stack in the opposite direction. That made things considerably easier. Long knob slide, no worries about the shellcode self-destruction, and generally less space restrictions for the exploit. Confession time. I didn't do this deliberately. That was not the reason why I did this, at least not consciously. As I mentioned, I did run into these issues myself, and there could be some kind of evolution going on, you know. I knew which approaches kind of like worked for me, so I kept doing the approaches that worked. Maybe I've just seen a good tutorial that was doing it this way already and I just did it exactly that way, or maybe I noticed that this is what works and so I kept just doing that. But I really appreciate this comment and especially this analysis comparing my approach to his approach. Both are valid, both work, but there's this like small caveat that has such a big impact. So he also basically had the setup. He placed the shellcode stuff before overriding RIP. This means there's limited space in here. Now here we had like 256 bytes until we overwrite RIP, so there's plenty of space. But maybe your buffer is smaller, maybe just 64 bytes, 32 bytes, 8 bytes. And then obviously you don't really have a lot of space for shellcode before you overwrite the return pointer. You can fix this code here by moving the shellcode further away from RIP in this direction. So for example, you could either trade the padding and the shellcode, and then obviously you need to also adjust RIP so that it points now all the way at the start here. Or you could do like a combination. You could do a knob slide first here, and then this padding gets a bit smaller again. But again, you must be careful that the shellcode doesn't get too close to where RIP is. And the reason why I say where RIP is because this is also where the stack pointer is. RIP was popped from the stack, so this is right now where the stack pointer is pointing to. This is the location of the stack pointer. So you can just be careful to move further away. If your shellcode doesn't really use push instruction, then this is also less of a concern. But the alternative technique, that's also the technique that I used when I developed this exploit for the first time, which you can see in the video tomorrow. You place the padding, then RIP, and then your shellcode. You could even add a knob slide in here as well, just to move that thing away from the stack. And here I remove the calculation to make the previous one work. Now this points right at the start of the knob slide. And now we could like point this also a bit further in, like 10 bytes into the knob slide. And now it should work. It didn't. Oh, we have the CC. Let's replace the CC with a knob. Now it works. Now we have our root shell. Oh my gosh. Thank you, brain, for figuring this out immediately. So these were the 2 pitfalls that I had for you today. Be analytical when you receive a segmentation fault and analyze what exactly seg-faulted. And this is also how you can recognize a buffer overflow that might have not looked immediately like a buffer overflow to you. And the second issue is the corruption of shellcode on the stack, because obviously the stack is used for various different kinds of operations, and if you have your shellcode there, it might get overwritten or modified. Obviously, there are multiple ways how a program can write stuff into memory, and so you might have other ways that can corrupt things. You have, for example, simple move instructions that just happen to point right into where your shellcode is, so that could also corrupt your data. And of course, this also does not only affect shellcode, but could also affect a ROP chain. If something is corrupting that ROP chain, your exploit fails as well. That's all I got, and tomorrow you get the exploit walkthrough, how to develop this exploit in this case. If you want to already try it yourself, you find the code and how to compile it in the description. Oh, fuck. I'm getting sick and I'm not done yet with my 24 videos for Hexember. So wish me luck.